Hello, calculus students. This is a short video talking about implicit differentiation and giving a few example problems to show you the process. The reason that we have to consider a new form of taking the derivative is because when we have relations of x and y variables that create the pictures you can see here, which are not functions because they don't pass the vertical line test. If I draw a vertical line here, that line is intersecting the graph in three separate points. Similarly, for this parabola turned sideways or a circle, any vertical line that I draw is intersecting the graph in multiple locations. The way that we know how to take a derivative currently is just for something which is a function. So with this circle here, we could go through the trouble of defining it as two separate pieces. One of the functions being up here, and then a different function being down here. And we would give them two different delineations so that we could take the derivative of them individually. This one here on the right, we did this example in class, and we showed that we could find the slope at a particular point on the graph. In this case, we used this second function down here. But rather than having to define a function in multiple locations, especially with this one that's given first, I mean, we really would have to define this in three separate places. That would be maybe one of them, and here being another, and then maybe this would be a different part. I guess that could, the way they have this drawn, they've got that as part of that other function. They have this here. So they have three separate functions being defined. We use implicit differentiation instead, which allows us to take the derivative directly of the function without having to break it into these component parts. So this looks really simplistic, the way that this is spelled out. We're going to take the derivative of both sides of an equation with respect to x being the independent variable, the one that's in charge. And we're going to, when we do so, every time that we take the derivative of any component that has y in it, we have to tack on a dy dx, saying we're taking the derivative of y with respect to x. Meaning that if we could rewrite a function in terms of y of x equals something, x is the variable that's being plugged into the function, and y is the output value. So this is the input value, and this is the output value. Once we take the derivative, we have to take any of the terms that have a dy dx, collect them all onto one side so we can factor them out, and solve for dy dx. So we want to end up with a final product of dy over dx equals, and then whatever our equation is. So we'll go through three examples showing how this happens. So let's consider the function or the relation x cubed plus y cubed equals 18xy. Rather than having to try and solve this equation to be y equals everything else, I'm going to take the derivative of each term directly and then add on any additional components as needed. So for this first term, x cubed, the derivative with respect to x is 3x squared, using the power rule, bringing the power down in front, dropping it by 1. And technically, I have just taken the derivative of x with respect to x. Looking at the second term, similarly, I would have 3y squared. I have just taken the derivative of y with respect to x. Again, we are trying to find dy dx. And so this is the variable that we are saying is the one in charge, the one that we're taking the derivative with respect to. This denotes the function. So with respect to x. When I look at the right side of this equation, I need to use the product rule. Let's consider this to be the first function, and then let's consider this to be the second function. So using the product rule, I'm going to take the first function and multiply it by the derivative of the second function. The derivative of y is 1 dy dx. I have to tack the dy dx on because I just took the derivative of y with respect to x. Again, this is the first function, and this is the derivative of the second function. And we'll add to that the second function, which is y, and we'll multiply it by the derivative of the first function, which is 18. Technically, it's 18 dx dx. We just took the derivative of x with respect to x. Now, this dx dx we don't usually write. We don't usually write this because it's just equal to 1. So as we move forward, I'm not going to write that part. What you need to remember is just to add on a dy dx anytime you take the derivative of a term that has a y included in it. All right, next step is to collect all the terms that have dy dx on one side of the equation and anything that doesn't on the other side. So let me simplify this a little bit first. Let's see. We'll have 3x squared plus 3y squared dy dx equals 18x dy dx plus 18y. Okay, I'm going to move this term over to the left, and I'm going to move this term over to the right so I can collect the dy dx's. So we'll have 3x squared minus 18y, and then I have 18x dy dx minus 3y squared dy dx. On the right-hand side, I'll factor the dy dx's out to the front. So then I can divide both sides by by this whole thing. Hang on a second. There we go. I'm going to divide both sides by this so that I can get my final answer. It looks like all of these terms are divisible by 3. So let's do one final step. That'll be a 6. And this is our final answer. This will allow us to take the derivative for this original relation we had anywhere on the curve to be able to find the tangent line. Again, without having to separate this into multiple individual functions. Okay, let's look at a second example. Let's consider y squared equals x minus 1 over x plus 1. Because this has a quotient in it, we're going to use the quotient rule on the right-hand side. On the left-hand side, we take the derivative and we have 2y, and we tack on dy dx because we've taken the derivative of the variable that's not the one we're taking derivative with respect to. So dy dx gets tacked on. On the right-hand side, we're going to write the bottom function times the derivative of a function on the top. The function on the top has a derivative of just 1. This is the bottom function. The bottom function also has a derivative of 1. Technically, it would be 1 dx dx, but we don't write that dx dx because it doesn't add any value, right? So this is the bottom function multiplied by the derivative of the top, which would just be a 1, minus the top function times the derivative of the bottom. So x minus 1 times 1. And then we divide by the function on the bottom squared. Looking at this whole numerator, the x's are going to cancel, and then I'm going to have a 1 plus 1. So that's going to combine to be 2 over x plus 1, the quantity squared. And then I will divide both sides by that 2y. And the 2's will cancel. So it looks like for our final answer, we'll get 1 over y times the quantity of x plus 1 squared. All right, let's look at one more example. Let's consider the relation 3xy plus 7, the quantity squared, equaling 6y. Looking at the function on the left, I'm going to have to use the chain rule. The idea will be to bring the 2 down into the front, drop this power down by 1, but then I have to add on. The chain rule says I need to consider what the derivative of the inside is going to be. So before we get started, let's do a little bit of side work over here. Let's consider what is the derivative of the inside part. Inside the parentheses. Let's see, I'm going to use the product rule for this, right? First, second. Let me move this down. Hang on a second. Let's see if I can move this down. There we go. All right, so I'll take the first function, 3x, times the derivative of the second, which would be dy dx. Technically, the derivative of y is just 1, but we'll put dy dx, 1 times dy dx, plus the second function, which is y, times the derivative of the first. So the second function is y, and the derivative of the first function is 3, the first function being 3x. And then that plus 7 on the end, we're just going to add a 0. So because 7 is a constant, that's not going to add anything. So it looks like the derivative of the inside here is going to be 3x dy dx plus 3y. So this is just kind of something we're doing on the side here. All right, so let's go back to our original problem here. Scoot this guy over a little bit. All right, so taking the derivative, we're going to have the 2 come down into the front, and then we write what's inside the parentheses just as we see it. The power gets dropped down by 1. And then we're going to tack on the derivative of the inside, and that's what we have over here. That's what we found over here. So we're going to tack on a 3x dy dx plus 3y. So we're using the chain rule. And then on the right-hand side, the derivative of 6y is 6, and we tack on the dy dx. All right, I'm going to first distribute the 2 to get 6xy plus 14. And then I'm going to distribute, I've got to multiply this binomial out because I've got to separate the dy dx's. So multiplying this first, we get 18x squared y dy dx. Then multiplying this, we get plus 18xy squared. Then here, plus 42x. And then here, plus 42y. Okay, so we'll move this guy over to the right and this guy over to the right. So that we can factor the dy dx out of each of these terms. And then we'll be able to divide both sides by this whole thing that's in parentheses. This should be a minus, right? Let me just double check. This should be a minus. Let me just double check my math here. Okay, I think that looks good. Then I will divide both sides. And it looks like each of these terms is divisible by 6. So let's do that. And I think this is our final answer. I stated in class that these are problems that you just have to practice quite a bit. And so I will put practice problems for you to do on our homework set and bring lots of questions to class. Thanks for watching, and I'll see you in class.